All right, let's get started. Again, welcome to everyone who's joined us today. I'm Samantha Link, and I'll be moderating today's webinar for the latest innovation from Gecko Robotics, TOKA Flex. As we go through the presentation, all attendees will be muted, but please be sure to send in questions through the Q&A located at the bottom of your Zoom webinar screen. I'd like to go ahead and introduce our presenter and Director of Engineering here at Gecko, Ed Bryner. Ed has been at Gecko for 5 years and has been through 30 iterations of the robotic technology since. Ed was an electronics engineer for the Airborne Anti-Submarine Warfare Division with the DoD, and now has extensive technical knowledge and experience in robotic solutions for clients in industrial industries across the globe. You may recognize Ed as an honoree of Pittsburgh's Top 30 Under 30, as well as his contributions in publications and organizations like Inspectioneering Journal and ASME. He's going to take us through the details on the newest robot, TOKA Flex, today, alongside of a live demo. So let's all welcome Ed.
Thanks a lot, Sam. Really appreciate the intro. I'm really looking forward to talking to everybody today about TOKA Flex. As Sam said, we're going to go through a couple different steps for this presentation, giving a broad overview of some of the different technical specs, moving into a technical demo, and then talking about one of my favorite subjects, ultimately what comes off of the robot, our data. So getting into that, what is TOKA Flex? Our TOKA Flex is really our most advanced robotic system to date. It builds upon all of the different building blocks that Gecko Robotics has been working hard to develop over the last several years, from many of the different robots that have probably been on some of your sites and facilities and assets, from the TOKA 3, the TOKA 4, the AVA, and beyond. But the TOKA Flex builds on the modularity and adaptability of deploying ultrasonics to very tough to reach places. And it's really a rugged platform that's built on many of the foundational elements of those other systems. We utilize an advanced data acquisition system to be able to pulse several different ultrasonic transducers across our array that we commonly call iSense. And that array holds our RUG deployment, ultimately allowing us to catch and capture the different defects that we're trying to find on your various assets. This system is meant to be very flexible and adaptable, and we'll show you all of the reasons and all of the foundation that is built into this particular platform. So getting into those technical specs. TOKA Flex was designed to have various RUG systems placed onto the front of rapid ultrasonic gridding. For those that are unfamiliar with RUG, and there's several articles that you can read on Inspectioneering about this, but 12 to 24 single element transducers. Generally, we deploy high frequency, 10 megahertz, 5 megahertz, 7.5 megahertz, different transducers on the front of this system, depending on the asset. And the RUG deployment generally has anywhere between 1/4 inch and an inch spacing. So you can think about many of the different technologies that are deployed today, AUT, et cetera, where a raster arm scans horizontally across the asset and then vertically climbs. With RUG, what you're utilizing is the advanced electronic technique of pulsing across in a non-mechanical way, but rastering and pinging each of those sensors in an electronic way, and then utilizing the power of multi-channel systems to be able to capture high fidelity data in a very similar fashion by increasing your system PRF. And that system PRF ultimately gets you the data density that is needed to be able to detect and be able to annotate the different damage mechanisms that you generally see in these piping pressure vessel type scenarios. This particular system is made to climb about 75 feet and beyond. And that system utilizes rare earth magnets, neodymium rare earth magnets, to be able to attach itself to many carbon steel and duplex assets. In general, we built this system to have a very flexible suspension. It's one of the toughest technical challenges that we've worked on to date on this particular platform. And ultimately, it can adapt down to a 6-inch diameter pipe to perform an OD inspection all the way up to a flat surface. We've also built this system to be extremely rugged and actually be able to self-cool itself and be able to perform online inspections up to 275 degrees Fahrenheit and be able to survive temperatures above that if we were talking about a blow line. But generally, while the inspection is performing, we've tested the system up to 275 degrees. And one of the advantages of RUG, as all of you know, is our production rate. Our production rate can go much higher, up to 30 square feet per minute, and utilized as a quantitative scanning tool so that you can deploy many of the other more advanced techniques to be able to do that localized scanning, high resolution imaging as well. Getting into why we've done this and some of the different pieces of the independent suspension that I spoke to earlier, the flexibility that's built into that, the hard technical challenge. We knew that we needed a very flexible, very robust robot to be able to get into many of the diverse assets and asset classes that this system has to be able to perform so that the robot can go from asset to asset in the time of a single shift or in the time of a single week. Turnarounds are extremely critical, and timing of all of that event is really important. And finding a bunch of different robotic systems to perform every different asset class is unacceptable in order to be able to make sure that your time to inspect is as low as possible. And so we've built this suspension to be able to adapt from 6 inches all the way to a flat surface, thus giving us a wide variety of asset classes that we can deploy this system on and be able to capture high fidelity, high resolution data. As mentioned, each one of the magnetic wheels is actually on an independent drive axis, which allows for a great maneuverability and adaptability that hasn't been seen really with our TOKA platforms to date. This system is the most flexible and ultimately most maneuverable system to get into very hard to reach areas, including, and we'll show a couple of videos today and a live demo of navigating over the extradose and intradose of elbows, a particularly tough place to reach and honestly a place that we have seen high wear, especially on that extradose of many of these piping circuits. We've overcome an ability to be able to go over weld lines, including with our sensors and the ability to have our sensors restabilize themselves after going over an obstacle, all the way up to a 3/8 of an inch or 10 millimeter obstacle. This could include weld lines, repairs, plates, etc. And ultimately, the system is made to be able to do 180-degree turns to maneuver around inlets, other obstacles, supports, etc.
So there's a question here. How does TOKA Flex perform on piping with lead-based primers, both magnetically and navigationally versus ultrasonically?
Yeah, absolutely. So there's a couple key components that are built into our system. We actually have some tires that are attached to our magnetic system to protect your coatings first. Obviously, those are there for with intention and reason. And ultimately, much like all other ultrasonic systems, we do use an immersion-based technique to be able to capture our ultrasonic data. But generally, we deal with coatings much like many other ultrasonic techniques. The better the coating is coupled to the surface, the better your data is going to be. And depending on that coating, if you do have concerns over your particular coating, we have extensive subject matter experts and people in-house in lab that we can take your samples and actually be able to test those in-house prior to coming out to site to verify that your coating is not going to interfere with the reliability and robustness of our inspection as well. Awesome, thanks, Sam. Keep the questions coming. Really looking forward to making this as interactive as possible. So I don't feel like I'm talking to you, but talking with you. Our heat hardened sensors is one of the things that we'd love to talk a little bit about today, because I know this is a really critical subject. How can you perform inspections before you're actually in the turnaround is one of the pieces that a lot of feedback has come back to us. If you were able to have the data and be able to be better prepared for the turnaround to perform your maintenance and reliability workflows, ultimately you'll be in a better place. And so we've built this system to be able to climb on in-service units up to 275 degrees. And generally the system actually will be able to survive on things like blow lines, which may go over that 275 degrees. Ultimately, we would pause the system, wait for that blow line to come into a state where you're no longer blowing, and then be able to continue that inspection. Our operators are trained inside of their standard operating procedures to ensure that they're calibrating the system to the material that the heat and the material that you're ultimately going to be performing that inspection on. That works very, very similar to all traditional ultrasonics and ensuring that you're going to get high accurate data. The actual robotics system self-cools itself, as I was talking about, actually utilizing certain portions of the coupling feed to be able to cool the various drive modules and the data acquisition system as it climbs around your asset. On the left, you're seeing one of the many tests that we performed on an online inspection with this TOKA Flex system. Getting into some of the fun areas of the maneuverability of the system is talking about the capability of the system to be able to do intradose and extradose of piping, one of the very hard to reach areas generally for robotics. This system's built to ultimately sweep over many different types of elbows, not all to date, but we're continuing to develop on top of this platform to push it to its limits. And so many of the different assets that we're able to do, and we can do a geometric study with you and many of our mechanical engineers, but ultimately swept elbows on 10-inch diameter piping, as well as anything that is over a 20-inch curvature is capable for this particular robot. On the left-hand side, you see exactly that, a robot climbing, doing both the extradose and intradose. Ultimately, the system is also able to climb up to about 75 feet. The reason we actually picked that number is, in general, there might be locations that you have to climb over 100 feet, but the system is made to allow you to deploy it in many different regions, many different ways from various platforms. And through our studies and through all of the asset configurations that we have investigated, the ability to actually deploy from a platform or a JLG ultimately allows us to remove the tether weight and make sure that we're performing an exceptionally safe inspection for you. One of our very important core values here at Gecko. Ultimately, we want to be able to make sure that the robot is extremely safe and reliable while on site. And that's a very critical piece to why we've picked that 75-foot height number. And ultimately, the access points for that are really critical, and our operations team would work with you to make sure that that works to your favor and your advantage. Moving into the remote visual system, on the front of our inspection units, we are actually deploying a couple different types of non-destructive testing. Generally, the most requested is obviously our ultrasonic inspections, but we also deploy on the front of iSense and in front of the TOKA Flex, this very high fidelity image as well. Generally, these images are taken at 2K resolution, and we take about an image per side of the robot every foot. This allows for a couple different things. Obviously, a visual aid as you're continuing, but it's also really important for us that image and the ultrasonic data that you're actually taking post-inspection. And so you're able to utilize this data as a visual inspection, but also an area to orient yourself around as you move through our portal. And we'll talk about that later today as well, as what does that interaction look like and how do you see these images as well as your ultrasonic data inside of our interactive map that's provided.
So a quick question here is, how clean does the surface need to be?
Yeah, Sam, that's a great question. In general, the best rule of thumb, the best practice is the cleaner the surface, the better your results will be. That means that you're going to have superior coupling and ultimately allow for the highest resolution data possible to make sure that we're ultimately not losing any type of access to subsurface defects. Now, with our system, we have many different images that we can show you where the surface was not optimally cleaned or prepared, but because we're using spherically focused immersion-based technique, we're generally able to couple to the surface a little better than a contact transducer. And that was picked for a reason that we're performing these automated inspections. And so I think we quote a couple cleanliness standards that we generally like to see for the most robust and reliable inspection. But as you saw in the last picture or in the last frame, the surface was not perfect. Some of the actual coating here is chipping away over time or degrading over time due to weather and other forms and factors. And we were able to perform and collect a very robust data set even on an asset such as this. Any other questions, Sam, before we move on? Awesome.
Actually, yeah, one just
so
came in.
We wanted to,
sorry. Have you ever done any stack inspections on biomass boiler furnaces? Sorry.
Have we, so biomass furnaces specifically? I'd have to go back and look. Stacks. Sorry. Yeah, so we have done, good. Yeah, so we have done various stacks and liners, et cetera. It really depends on the asset configuration. We have done some biomass plants as well. Specific to the asset configuration, we would want to set up a time to either do a walk down with our sales and operations team to verify and validate the drawings and the asset actually match to make sure that this inspection is going to perform to your expectations. But yes, we have done stacks, we've done liners, we've done various asset classes, and this platform would be able to do those as well. Awesome. So getting into a couple of the field tests that we've performed for this particular asset, one of the big Gecko beliefs, one of my core values is, and I share this with the rest of the team, is ultimately I don't want to build something that is just considered a lab robot. I want to make sure that our team is deploying these systems and testing these systems in the environment that they are ultimately going to be deployed, because these environments can be harsh. They can be very difficult to replicate inside of a lab. And so this is a really critical piece of our development cycle, is actually working with many of our power users, our most innovative users, our early adopters, to ultimately deploy this system and get it field tested early and often. So going into this, one of the things that many of our engineers do is ultimately take their developments, take many of their early concepts out to the field. And we look for many of the trickiest and most difficult access points to be able to run these early experiments and rugged testing. And that field validation is a very critical phase gate for us to ensure when we ultimately hand this over to our operations team, that our engineers know that this system will be reliable for both our operations team and our customers. And so moving into what have we actually deployed so far? Over the 9 months that we've been developing this system, we've had a total of 16,000 hours in development, and many of those hours were spent deploying the system in various asset classes. We've iterated several times. Actually, on the right here, we're looking at one of the early beta units of the TOKA Flex. I can tell that because of the color of the system being red, versus what you'll see today, which is a clear anodized robotic system that we'll demo for you. But this was one of the early units that we wanted to get out, ultimately make sure that our early developments were working, reliable, and ultimately be able to maneuver inside of and be deployed on many of the different assets. We've deployed so far on an overhead crude line, or actually a couple overhead crude lines, various piping 8 to 10 inches, as well as a heat exchanger with undisclosed customer who's been really great in helping us to co-innovate on this particular platform. We've also worked inside of a pulp and paper plant, specifically around digester piping and blow lines, which was a very, very tricky asset to continue to innovate and integrate on, especially as the system is blowing while you're doing an online inspection. Those temperatures can easily rise well above 275 degrees Fahrenheit, and testing that in-house on piping, that's really hard to keep the heat capacity high enough while we're running our robot in a lab. We were able to do a lot of learning on site where the heat capacity of those particular assets remains a lot hotter as you continue to pour couplant over the surface, as an example. And finally, inside of the power generation industry, we've already deployed on several water lines, fuel oil piping, and air receiver tanks as well. Various asset classes that this TOKA Flex has already been on, validated and verified through our field engineering team and field deployed team. to ultimately be able to make sure that we were innovating and integrating into the environments that this system will ultimately be inspecting. So by the numbers, over this 9 months for this particular platform where we integrated many of our core foundational elements of the other TOKA systems into our TOKA Flex, we've also done 16 site visits, over 8,300 feet of inspected piping and other assets, 8.2 million A scans recorded, and many of those, up to 25% of those, were at 250 degrees Fahrenheit and above, showing that we didn't just test this platform on all offline assets, we did several of them online as well. So next we're going to hop into a live demo. Actually, why don't I pause here? Sam, are there any questions that I can answer before we get into the live demo?
No questions right this moment, but let's go ahead and flip the screen to a live stream happening in Gecko's testing facility located in our Pittsburgh headquarters, where field engineers have TOKA Flex up on an asset and ready to go.
Awesome. So perfect. So I think I'm seeing the video feed, so I hope you all can see it as well. What you're seeing here is our TOKA Flex. The TOKA Flex is currently working on a pipe inside of one of our Pittsburgh lab environments. So we do have lab assets that are representative of the systems that this platform is made to inspect. Right now, we're running on the side of a what looks to be a 24 or 48 inch pipe. And you can see how the suspension and each one of the drive modules on the right and left of the robot are fixed to our suspension underneath, which actually allows for our encoder to sit on the surface of the asset as well. On the front of the robot, what we're looking at right now is the iSense RUG, Rapid Ultrasonic Gridding Array. Each one of those elements has its own couplant feed, feeding into our sled design. It's now approaching a representative obstacle that you'll see the actual iSense system be able to climb over and ultimately reconfigure its stabilization so that all of those sensors can continuously take readings as it not only surmounts that obstacle, but as it goes back over it as well. And you see the drive modules themselves are able to overcome that obstacle with ease as well, and climb back and forth over that particular system. Above that, you see the actual center body and the deployment handles above, as well as all the connectors for the various UT sensors that we can plug into. Couple other points that generally have been asked to me before. What is the standoff of this particular robot? The standoff of all of our robots are designed to be able to have OSHA compliant scaffolding built around the asset without the robot interfering with that. Generally, that's 10 to 12 inches. So this particular robot, no matter what size pipe it is on, the suspension will ensure that as long as 10 inches is provided between scaffolding or any other obstacle above the system, you'll be able to climb under that and be able to continuously collect data. If there are obstacles, maybe inside of a various pipe structure, you might ultimately need to be able to have the array move to the left or right. You can swing that entire arm assembly all the way to the right or left, ultimately allowing for you to increase your coverage in many of those areas that have obstacles that maybe butt up right against the pipe, as an example. And now you're starting to see the robot make some nice transitions. So you saw from the side of the pipe there, ultimately on top, that transition was extremely easy, and you see that all of those sensors are still making contact with this particular asset. And here we're starting to go over the extra dose of a pipe. So with relative ease, the system's able to go over this extra dose on this pipe elbow And we're coming back up and over top of the pipe elbow as well. So one of the advantages of this particular system, you see our array bar is actually conformed to the asset as well, ultimately allowing for us to collect high fidelity data. Pretty cool shot here of the robot coming up over that elbow and coming down into a vertical space. And a little zoom in for show on all of the cables and connectors to enable that electronic rastering across each one of those systems. A couple questions have been asked around why quarter inch or why 1 inch spacing. Ultimately, because we're able to get the system PRF with our advanced data acquisition system high enough, ultimately we're able to make sure that in the Y direction, in the travel direction that the robot is coming to and from us, we're able to ping the surface as fast as a traditional system in the AUT space. So we could have an A-scan up to or greater than 40 mils based on the travel speed of the robot and ultimately the resolution that our customer is looking for. And that's a really, really critical piece of this as well. Ultimately, that 1 inch spacing or that quarter inch spacing, the beams between each of those particular single element transducers ultimately allow for a similar resolution at faster speeds than traditional tools on the market. Awesome. Sam, any questions that are coming through that I can answer?
Well, I wondered if for the live demo, any chance that they could show us some maneuverability with the robot? So maybe some turns, just speed in general?
Yeah, sure. So Wes, I think you can hear me, and Sam, could you take us through, and Wes is one of our field engineers driving the robot right there. Could you do a maneuver to the side of the pipe, maybe go down and underneath and have the system upside down? So you see, he just avoided the obstacle entirely there. Instead of going over it, he's going to take the system around the side of the asset and ultimately all the way underneath. It really shows that this system is, and you can see here that the independent suspensions on all of those array, on each of those sensors is ultimately still able to remain in contact and aligned. And so as long as the coupling feed is secure, you're able to maintain that coupling all the way through that transition, reposition for the next run, and ensure that the data quality is going to be high on the live feed of the laptop that's connected to this system. So you can see here very quickly, we've already transitioned from the top to the side to ultimately the bottom. We are running upside down on this particular unit. Each one of our magnetic wheels is over-engineered to ensure that this system won't peel off. In certain configurations, maybe you have a non-carbon steel asset like a duplex. There may be engineering reasons to add various safety measures based on your particular safety team. This system does have attachments for lanyards as well as fall arrest systems that we've built to ensure that this system is safety compliant based on your safety regulations of your industry and your site. But you can see here that the system is able to carry itself and a much heavier payload to be able to ensure that we're able to stay on the asset as we continue to inspect.
Great. So we have some questions that have come in.
Sure.
Clearance around surface. How tall is TOKA Flex?
Yeah, it's a great question. So TOKA Flex can ultimately fit under any OSHA approved scaffolding. Generally all of our TOKA units, this is a consistent constraint that we put on our engineering team to ensure that it fits under anything that is 10 inches from the surface. So on any configuration, now you'll imagine because we have an adaptable suspension that your standoff changes a little bit. Generally that can fall below 9 inches, but we ask to stay inside of that OSHA configuration. The iSense rail, the sensors on the front of the robot can swing left and right all the way to the edge of the robot. So if there is a place where something falls below that 10 inches, ultimately the operators on site will configure the robot almost like an extendable arm off the side to be able to go under those more constrained areas.
And what is the diameter range that it can traverse on?
Yeah, so the diameter range for this particular system is anywhere from down to 6 inches OD all the way up to a flat surface. So one of the reasons that we've made such an adaptable suspension for this particular robot is that we want it to be able to perform many different types of inspections while on site, whether it be tank shells, pressure vessels. But the beauty of this is it can go onto many different piping circuits, as long as we're able to attach to the outside of the asset while we're inspecting.
And can it run over welds? And if so, how thick do you foresee it will max out at?
Yeah. So the system is designed to go over anything that has a 3/8 of an inch standoff. Traditionally, many of the weld lines that we're inspecting over fall below that. That's and you can see here an obstacle very similar to a weld line. And actually, this obstacle that we're climbing over is a non-ferrous obstacle. It's aluminum representative weld line or plate. And our system is able to climb over, and you can actually see both the sensors have a suspension as well as the robotic system itself to make sure that it can safely climb over and climb back over in the reverse direction as well.
Awesome. Well, it's great for the demo. I think this is a great time for us to jump back into the presentation. So thanks for Wes down in the operations space. And then any other questions that come in on the robot, please feel free to send them in through the Q&A feature, and we'll make sure to answer them after the presentation is over.
Very good. So hopping back in, I'd love to just talk a little bit about not just the robot itself, but really what is Gecko doing for you. So if I go back to sharing my screen here, at the end of the day, we really understand that Gecko is not just a robotics company. We are ultimately trying to be and partner with our clients and our customers to really radically change how reliability and maintenance are done on many of our most critical infrastructure assets. And a big part of what comes off of the robot is our data. And so as we start to talk about downstream from our robotic solutions, what are we providing in terms of innovation here as well? Right now, we have another team of engineers, many different software engineers working really hard to continue to innovate on the data that we are collecting, both in terms of the robotic metadata, all of the localization information, temperature information, et cetera, that comes from the robot itself, but as well as all of the integrity data, all of the non-destructive testing data that we're collecting as we do an inspection. So I know that there was probably a couple questions on what is the robot ultimately connected to. That tether, as we're performing an inspection, is simply a communications couplet and power line. The power line is really critical. Obviously, we don't want a battery-powered system because these inspections could last all day. It could be a 12-hour shift where we're actually performing thousands of feet of line where we're collecting data. but the communication line is general Ethernet or fiber. That tether can actually be quite long, but generally we don't want more than 75 feet of tether weight hanging on the robot. So we make sure that operationally we tie off the tether in various points from various platforms whenever needed when it's climbing over that height. But ultimately the inspection is run from a laptop. Our data acquisition system is actually very uniquely integrated inside of the platform. The reason for that is ultimately it allows for the UT cable length to be very short, ensuring that the signal to noise ratio is very, very strong. The actual UT cable is very, very short from sensor to data acquisition system. So the analog travel of the signal is rather short compared to many of the other systems on the market. And ultimately that allows for our communication link to happen over traditional Ethernet. Ultimately, that's connected to a laptop where we have our software that collects every single A-scan that we are acquiring over the length of a run. An operator is able to look at many different views while they actually perform this inspection, both looking at the real-time A-scans, B-scans, and ultimately a C-scan of all of the runs stitched together from the robotic system to ensure that there's high validation and verification that we ultimately have collected all of the asset information that we need to during the inspection. And once that has been done and ensured we've acquired high quality data, the UT professional will actually connect that laptop to the internet and push all of that data and back it up on the cloud. Ultimately, we have several tools there where UT level 3 will review all of the data and the report that is generated by the on-site UT professional to make sure that the sign off for a high quality inspection has occurred and all standard operating procedures have been followed. And then one of the very unique things about our platform is because we have all of the robotic localization and metadata, we are able to create a web application deliverable for you that is an interactive map. This allows you to filter certain data. Maybe you have a team that you're really, really concerned about that you want to manipulate and create a report for yourself. This is really, really critical. And maybe you want to annotate year over year a very particular location that you want to do corrosion monitoring for. All of those tools are actually built into our portal, and we'd love for anybody that's really interested and hasn't seen our software applications to date to schedule a meet and greet with our various sales and marketing team, ultimately to be able to play around inside of this portal because the interactive nature allows you to do many different planning inspections. Maybe you're working on an RBI program or fitness for service for this particular asset, and many of the outputs are geared towards enabling better data-driven decisions from this workflow. Talking a little bit about our interactive maps and where we're ultimately going. We know how difficult it is sometimes to receive we've received the feedback that receiving just a PDF or a paper version of a report is very tough sometimes to understand spatially where we've taken that data, what operationally would have maybe caused this particular form or degradation. And we are heading down the path of being able to help you with your digital transformation, ultimately allowing you to spatially understand where our inspection data fits into the rest of your plant. And we want you to be able to interact with that data, filter to the lowest readings, understand what underlying reasons may have existed. Maybe it's a pre-existing condition, maybe it's a change in how you're operating that ultimately is allowing for this corrosion to progress. And this really deals with high fidelity year-over-year annotations, fitness for service determinations, bringing in professional engineers to be able to look at this data in new and unique ways. And we have set up our entire data pipeline to enable that for you. So with that, I wanted to make sure that I gave my contact information today as well. My email address and phone number are attached to this slide right here. I'd be more than happy to answer any more in-depth questions that you might have in the future. I'm sure we can hang on online to answer them, some of them verbally as well, but I definitely wanted to extend the courtesy that I want our engineers ultimately at Gecko to be interacting with our engaged customers. It's a really important piece of getting our engineers into the field, understanding the problem spaces that you all are feeling and want solved for you. And we want to partner with you to solve some of those toughest challenges. So with that, I really wanted to thank everybody for their time and answer any questions.
Great, thanks, Ed. So this has been really exciting information. Thanks to Wes and the crew in the testing space for showing off the robot for us. Let's go ahead and get started with some questions from the attendees. Just as a reminder, if you do have a question for us to answer right now after watching this presentation, feel free to send them via the Q&A feature located at the bottom of your Zoom screen. So just some general ones here that came off of the demo. Does the operator need to be within line of sight of the robot?
It's a great question. So I'm actually, I'm gonna scroll back up here just for a moment so that you can see the front of the robot. And I'll actually just really quickly turn on an ability so that you can see, hopefully, Sam, you can see my mouse here. So the robotic system has several different cameras on board. Obviously, these two cameras right here are going to be our inspection cameras. But you'll notice that we actually apply a very low latency camera on the front of the robot as well. Generally, this is a driving camera. This is using what's called a broadcast. It's either SDI or TVI camera. Very, very similar to, for any NFL fans that are out there, this is very similar to the pylon cam, where they're able to live stream from a pylon. And this is a very robust camera that's built on the front of our robot, very low latency, so that ultimately any response that's happening on the screen, our robot operators are able to see that. That is with intention. There's obviously points and places where the robot has to be able to get around a very tricky asset corner, things like that, where the robot operator may actually lose sight of the robot. In that case, they're relying on this low latency camera to ensure that the robot is driving safely. In general, though, we do have 2 robot operators on site for each one of our inspections. That is with intent for safety and tether management as well. And so those particular secondary operators will generally make sure that they have line of sight and either a radio and or voice call to make sure that everything is performed safely for you.
Great. How long does it take to generate a deliverable or a report after an inspection?
Yeah, great question. So there are different stages of reporting that Gecko really believes in. One is we want to be able to provide on-site feedback. This is a really critical real-time feedback to the customer. And so many of our supervisors are constantly looking and finding ways to make sure that we use real-time deliverables, maybe in the form of written or verbal communication while we're collecting to make sure that you can start to stage equipment if needed for any repair that might happen. We also have, once the robot has pushed data to the cloud, we have an automated algorithm that does provide a real-time report at the end of every shift, about 30 minutes after the robot has collected all of its data. And all you need to do is talk to the supervisor to ensure that the quality of our data is high enough to be able to ensure that a real-time deliverable can be provided without having to maybe re-inspect any area that had poor surface conditions, as an example. In those cases, the operator is trained to work with the client to make sure that that area is either re-inspected with different surface conditions and or maybe that is a less critical area and we can move to the next part of the inspection. And then finally, the full data report is generally delivered between 24, 48, or 72 hours, depending on the asset and depending on the amount of data that we're collecting. So depending on your turnaround, depending on when you want to receive your PDF and portal access, you can work with our sales team to ensure that the right turnaround time is quoted for you and ultimately performed by our operations and data validation team.
How long is the UT cable?
Yeah, good question. So the UT cable itself is rather short. So you can actually see here on the robot itself that the connection point right here, these LEMO connectors, which are IP rated, the length from this point, this connection point, all the way down to these sensors on either end is actually the length of this cable. So depending on the width of your array, the cables will range anywhere from, and they're consistent across the entire array, but they'll range anywhere from 6 to 24 inches, depending on the asset configuration and how far we might actually have to move the array away from these connection points. That's rather short compared to many of the other UT cable length situations where you might be running with a data acquisition on the system on the ground, and then you're ultimately limited by signal loss over the length of that system up to the robotic platform itself.
How do you calibrate when the pipe is at an elevated temperature, or do you temperature correct in the program?
That's a great question. So we've built in both features. Generally, we like to perform and do both a calibration and verification at temperature whenever possible. Now, there are some different assets that are going to be potentially blowing and things like that, in which case we'll have to have a UT level 3 sign off on how we do the calibration, verification, and or post-processing. But generally, all of that is worked into the system. It does take a little bit more back and forth with you as the customer, depending on the asset and the temperatures that we may experience. But that is something that is written into our standard operating procedures, and we're more than happy to share those with you as well.
How important was client input in the design and development of TOKA Flex? Examples of unique or really hard industry-specific challenges?
Yeah, it's a great question. That's exactly why we actually developed this platform. Many of the direct feedback and partnering with our current clients and current what we like to call power users or really engaged innovators in the space, early adopters, as many talk about. Our earliest adopters really wanted to see something that was able to fit this part of the market, which generally has been, for the most part, unserved in a really robust and reliable way. And so we worked and partnered with several key customers, both actually in all three of our industries to date, oil and gas, pulp and paper, and power, to be able to deliver on this TOKA Flex. And many of those customers actually got to see early concepts of this particular system, allowed us to receive early and often feedback, and adjusted many of the things that you see today. I think one of the biggest challenges that we faced was actually the drive module and suspension of both the robot and the array that you see on the front. There were many hours, many concepts, many feedback sessions to make sure that we were both rugged and adaptable to the many different assets, and ultimately making sure that this TOKA Flex was flexible enough to be able to cover different asset classes. That allows for a lower logistics footprint when we show up on site and you need Gecko to actually inspect many different assets. We can show up with a single TOKA Flex or a couple TOKA Flexes to be able to do not just a piping circuit, but also a tank shell, or maybe even get inside of some of the other various asset classes like spheres, pressure vessels, et cetera. And that was one of the very key parts of iterating on this platform with our customers.
So what happens if the robot encounters a ferrous to non-ferrous interface?
Yeah, it's a great question. So generally, we follow up with many of our clients, and we have always wanted to make sure we see drawings and verify that we're not going to hit a purely stainless steel part of your asset. Now, if there are questions, if there are maybe lost paperwork, and we've experienced this in the past where they weren't sure certain repair was done in a certain material. Some of these facilities have actually, transitioned from owner to owner, and some of those reports have been lost over time. That's something where we'll add safety countermeasures like a fall arrest system to ensure that if we were to hit a patch like that, we would not cause any damage both to the asset, to the people around the particular inspection going on, as well as to the robot. Generally, this system is not made to climb on non-ferrous assets. Its way to connect to the asset is utilizing magnetics. And so that is one of the critical pieces. Now, there are certain alloys, duplexes, et cetera, that are ferrous enough for us to be able to perform a very similar inspection. But we would need to know that not just for the climbing safety, but obviously for the different speeds of sound that ultrasonics will experience if we are climbing on something that is not traditional carbon steel.
And how do you deal with interferences such as hangers?
Yeah, great question. So the system is really meant to be able to drive around many of the hangars that we have seen thus far. But how do you collect data as close or around many of those different pieces? Generally, there's always at least one run length that we can utilize for the robot to actually be able to maneuver around. Now, you might come up against a flange as an example. In that case, we might have to be able to put the robot on, inspect between flanges, and then pull the robot off. It's not going to be able to traverse a large flange. But the system is made and is width-wise small enough to be able to extend its array to the left or the right and be able to run straight. And we actually can shorten the array as well. So it doesn't have to be 1-inch spaced sensors by 12 sensors. We could drop that down to just a couple sensors to be able to get to those little final pieces of data that ultimately are really critical, maybe around a hanger or close to a joint, close to a bend that we're actually not able to traverse, as an example. Anywhere that we're not able to access with the robotic platform today, our on-site professionals can couple that service with many of our other technologies, including handheld inspections, to make sure that you have a full fidelity map of all of the critical access points. The biggest, and we want to make sure that that's a full service solution for you so that you don't feel like you have many different contractors showing up just to perform the same inspection that would have traditionally been done while coupled with our robotic technology.
Does the system generate a 3D model of the surfaces being tested or fuse it with an existing model?
Yeah, great question. This is something that we are constantly working on. And actually, I am currently looking for customers to partner with on this localization problem. This is a really, really critical thing for us to continue to innovate on. Today, what are we utilizing for localization? We're utilizing several different technologies that we are capturing, both encoders underneath, passive encoders inside of each of the drive modules, as well as different basic localization techniques of robotics, including IMU, the visual cameras, et cetera. But ultimately, we want to figure out a way that we are providing high fidelity information in terms of the space that we're collecting on. Right now, we utilize our maps and we map it to the 3D asset metadata. So the OD of the pipe, or maybe you have a CAD model that's already existing, and we can utilize that to wrap your data around that particular asset. In the future, though, I'm looking to continue to innovate with our team and with some of our engaged customers on what does that data mean to them. Maybe there are no longer CAD models of this particular asset, and we could be building that while we collect this information instead of using maybe a drone photogrammetry type technique. We could actually be utilizing all of the metadata from the robot that's physically attached to the system to be able to even see things like sag, et cetera. This is an area that we're really interested in at Gecko and looking to co-develop with those that are interested. So whoever asked that question, please reach out. Here, I'll go back down to my contact information, because this is a space that we actually have a dedicated team of robotic engineers, both on the software and hardware space, that we're continuing to understand why and what this data could be used for.
Awesome. So we're kind of coming to a close here. This question seems like the best one to save for the end. If they want a quote for an inspection project, can they contact you directly, Ed?
Absolutely. Feel free to contact me. I'd love to interface with you, obviously, as an engaged person with Gecko. If it's a service that you're looking for, I can absolutely get you in contact with the right people on our team to be able to schedule and project manage that. I probably will be involved. I'll be an informed party, but ultimately, from the engineering side, I am continuing to work with each of you to innovate on this particular platform and hopefully solve some of the problems that still haven't been solved to date for you. We really believe in serving our customers both from the engineering side and the operation side. And so having engaged customers both for both parties is really important to us.
Awesome. Thanks so much, Ed. Thanks everybody for joining us today. Just as a reminder, we will be sending out the recording to this presentation. It'll also be live on our website afterwards if you want to share it with colleagues. And in the meantime, keep on the lookout for the next upcoming webinars. See ya.